Let's solve this problem for finding the orthogonal basis set for this set of signals. Okay, so in this problem, as given in the slides and as given in the lecture document provided to you, we have an example of 4 such signals given to us. So this signal is called S1t, this signal is called S2t, and as per the slide, this signal is called S3t, and this is S4t. Okay, so we have 4 such signals for communication. So we are transmitting these 4 digital signals for our communication from transmitter to receiver. But we want to see what are these signals made of, or you can say what are these signals made of other orthogonal signals, just like usually vectors are made up of other basis vectors. So we want to find out the basis signals that constitute these 4 signals. Okay, so as per the process, if you remember, the step 1 was that we would find if there is some dependent signal over here, a signal that is not independent. So if you look at these signals, you'll notice that this S4 can simply be made if we add S1 and S3. So if we add these 2 signals, we get this signal S4. This means S4 is not linearly independent. So we will leave S4 because when we are done with finding the orthonormal basis set, then the orthogonal signals that made S1 and the orthogonal signals that made S3, they would also make S4. Okay, so we leave this one alone and we initially start with these 3 signals. Now you can pick any one of these 3 signals to start the problem. Okay, so you can either pick S1, S2 or S3. Let's pick S1. So we will start with S1. If you start with S2 or S3, you might have a different basis set. So that is why we studied in the lecture that the basis set might not be unique. Okay, so I will start with S1. So if I start with S1, if you remember, the first step is that I have to find a function f1 t, which is a function or a signal. And if you remember, this is the first orthogonal signal in the basis set. Okay, and what was the process of finding this out? I would take the first signal and I would divide it with its energy. Okay, energy of E1, under root of the energy. Okay, so this is a signal, this is a signal, this is a scalar value. Okay, so let's first find what is E1. So E1 is energy of this signal. So I will use this formula just for a reminder for calculating the energy of a signal. Okay, so I will integrate it from 0 to t by 3. T is over here, but the signal is not present from t by 3 to t. So I will integrate it from 0 up till t, and the magnitude of the signal is 1. So I will take a square of 1, which will be equal to 1, and I will integrate it. Okay, so as you can see, I will integrate it from up till t by 3 because it's up till t by 3. So if I integrate this equation, it's very simple. We will get the answer t by 3. So the energy of this signal is t by 3, and the under root of t by 3 is under root t by 3. So this is the answer of under root E1. So what do I do now? I have to divide S1 by under root E1 or under root t by 3. So the next step is this division. Okay, so I'll just divide this value. You will have to remember these values because I have very small space to solve this problem. I'll be rubbing off these statements very frequently. So divide S1 by under root t by 3. So this is S1. If I divide this signal by under root t by 3, I'll get another signal. So I will get another signal like this, just like this. Only the magnitude will be different. The magnitude will be 1 divided by under root t by 3. So the magnitude will be 1 divided by under root t by 3. So this will be the magnitude, or if you want to write it in a simpler way, you can write under root 3 by t. Okay, so this whole part is in the under root. So let's write it over here, 3 by t and whole under root. Okay, so this signal is f1. So this is the first orthogonal signal that I have found. Okay, so again a signal, and a scalar quantity. So this is f1, the first orthogonal signal. Now I wish to find f2, the second orthogonal signal. So if you remember the process correctly, there was an intermediate function or a temporary function called g2 that we needed to find out before finding out f2. Okay, so again I'll have to rub it off, but I think I'll draw it over here so that in future we might use it. So from 0 to t by 3, the value of this signal is under root 3 by t. Okay, so let's just rub it off now, and I want to find out f2t now. So to find out f2t, I need this intermediate function right now, and in this intermediate function, or the definition of this intermediate function was g2. It was that I need to subtract something from this second signal. So I pick up a second signal and I subtract the common area of this first orthogonal signal. Okay, so if I remove the content of first orthogonal signal from S2, the resultant signal is orthogonal to F1. Okay, so I just write F1 over here. So the resultant signal will be orthogonal to F1, and to make sure the signal, let's write T as well. So I remove S21 times F1t. Okay, so F1t is the orthogonal signal, S21 is the magnitude of second signal under the curve of the first orthogonal signal, and I'll remove this whole magnitude of first orthogonal signal from the second signal, so the resultant signal will be orthogonal to F1. That was the whole theory that we discussed in the previous lecture. Okay, so we already have F1, we have S2, we don't have S21. So let's just find out S21. Okay, so S21 was a scalar quantity. We had to multiply two signals and take an integral. So S21's mean second signal multiplied by one first orthogonal signal and taking the integral. Okay, so S2t is given over here. If we multiply this signal with this signal, you will see the common area is only between 0 and t by 3. From t by 3 up till 2 by and further onwards, this signal is absent. So multiplication of this 0 value with this part will result in a 0 signal. So if I multiply these two signals, I'll get a new signal which will look like this. It will have a value just from 0 to t by 3, and if I multiply the magnitude, 1 will get multiplied by under root 3 by 3, and the answer would be under root 3 by t. So this is the signal that has been formed because of the product of these two signals. Now I have to integrate it. So I'll integrate the signal from 0 to t by 3, from 0 to t by 3, and the value of this product is equal to under root 3t, 3 by t. Okay, so this is the case into dt. Okay, so this integral will give me a scalar value, that is S21. Okay, so if I solve this integral, the answer that I get is, I hope I can write it and you can see. Okay, I have a space till here. Okay, I get the answer under root t by 3. So I have S21 now, I have S2 and I have F1. So I'll just put these values back again. Okay, so just remember the value is under root t by 3. Okay, so the resultant answer will also be a signal. So S21, this signal is being subtracted from this signal, but I have to multiply this signal. I have to multiply this signal first with S21, which was equal to under root t by 3. So the magnitude of this signal is under root 3 by t, and the magnitude of this value is under root t by 3. So it will just cancel out. Okay, and I'll get the answer of 1. Okay, so because this value was under root t by 3 was being multiplied by under root 3 by t. So as you can see, the product of this under roots will get squared out, and t by will cancel out with t, and 3 will cancel out with 3, and I'll get an answer of 1. So this product made an answer of 1. But again, this is signal. It's a scalar quantity being multiplied by a signal, so I'll get a signal. This signal is being subtracted from this signal. So S2, from S2 I have to subtract this part. So you just have to subtract these two signals. This is from 0 to t by 3. So from 0 to t by 3, 1 will be subtracted from this signal. Okay. So from 0 to t by 3, 1 will be subtracted, and from t by 3 to 2t by 3, so from t by 3 up till 2 by 3, I'll have this signal still there. Okay. Now this signal is G2 of t. Okay. So what was the process of finding the orthogonal component? I have to divide G2 with its under root energy. Okay. So first we have to find out the energy of the signal. We will integrate it from t by 3 up till 2t by 3, and the magnitude is 1. So we'll take square of 1 into t of t. Okay. So what will be the product now? If you integrate it, you'll see the product is equal to the answer is equal to the answer of this integral is equal to t by 3. However, this is equal to the energy of the signal. I need to find out the under root of the energy of the signal. Okay, so once I find the under root of the energy of the signal, I divide the signal with the under root of its energy. So I'll divide this value with this. So I'll have a very similar looking signal, but the only difference is now it is from t by 3 up till 2 by t up till 2 into t by 3, and the magnitude will be 1 divided by under root t by 3. So when 1 divided by under root t by 3 comes, we can take the under root 3 up, and we'll get the answer similar to something like this. So this is how the answer will look like. So this is how, and that answer would be equal to F2. Okay. So when I divide this signal by its energies under root, I get F2. So F2 looks like this, or F2t looks like this. From t by 3 up till 2t by 3, it has a magnitude of under root 3 by t. Okay. So now I have second orthogonal signal. Okay. Now I need to find F3 of t. So if you remember from the lecture, how many orthogonal signals do I need to find? The answer is at most 4. Okay, because the total number of signals are 4. So I need to find out at most 4 signals, but maybe I can settle before 4 signals. Maybe at 4, maybe at 3, maybe 2, maybe 1. Maybe one orthogonal signal is enough. So you have to ask, can you make all these 3 signals by combination of these 2 signals? So I can make S1 with F1. I can make S2 with F1 and F2. If I add those 2 signals and multiply it with some value, I'll get this signal. So I can make S1, I can make S2, but I cannot make S3 because I have no signal over here that goes from 2t by 3 up till t. Okay, so I cannot make S3 from these signals. I cannot make S4 from these signals. So this means I need to find out F3t. So when I have enough orthogonal signals to make all these signals, I'll just stop over there. Okay, so this is the process of finding out these orthogonal signals. Okay, so the next step is finding F3t. Okay, so for F3t, we need to find another intermediate function. Okay, now I want you to solve this problem. I'll write down the equation, and I'm sure you can write it find these values very easily. So what I'm doing, I'm taking the third signal now and making sure that this signal is orthogonal to F1 and orthogonal to F2 by removing magnitude of these signals from this signal. So I'll remove the magnitude of third signal from the first orthogonal signal, and I have to multiply it with F1. Then I'll have to remove, this equation is going on, the magnitude the magnitude of third signal, I'll write it again. I'll remove magnitude of third signal from the in the area under the area of second orthogonal signal multiplied by the f2. So again, if you have vectors in mind, if you can compare, this scalar quantity is being multiplied by unit vector. Okay, so from one vector I am removing one of these dimensions. So I am doing this with signals, not with vectors. So the similarity is however there. So I need to remove these two signals to make sure that g of 3 is now orthogonal to f1 and f2. So just like before, we can find s31 and s32 in a very similar way. We will integrate s3, we'll first multiply it with f1 and you'll get a signal like we did before. You have to multiply this signal with this signal. Okay, and interesting, the result will be 0 because this goes from 0 to t by 3 and this goes from t by 3 to further. So the product of this signal will be equal to 0. Okay, so first you multiply and then you integrate to find this value, and for this case, and you put the limits accordingly wherever the function exists. Okay, so for this signal I'll multiply s3 with f2. So here is f2. So after multiplying these two signals, I'll get a new signal, and then accordingly to its limits I'll integrate this function. Okay, and I'll get s32. So now I have s3 over here, I have s31 and s32 from here, and f1 and f2 are already given. So I will draw and sketch this function as g3 then, and g3 will be orthogonal to f1 and f2. Then what will I do? I will divide the g3 signal, this whole function, with under root of the energy of g3. Okay, so I have the g3 signal. It's easy to find out the energy. Just take under root of that value and divide this signal with that value, and I'll get another signal. That signal will be called f3t. Okay, and you can find it out using this process for future reference. But if you can see over here, the first orthogonal signal moved from 0 to t by 3, the second moved from t by 3 to 2t by 3, and I'm sure you can see that the third signal will have a shape something like this. It will go from 2t by 3 up till t, and the magnitude will be same as before. What is the special in this under root 3 by t magnitude over here, here and here? All these signals have the same magnitude of under root 3 by t. The special thing is, if you find out energy of f1, if you find out energy of f2, if you find energy of f3, the answer is equal to 1. So the under root of 1, which means the under root of the energy of these signals, is 1. Why is this important? Because if you remember, in vectors, the under root of energy is equal to the length of the vector. So a length of a unit vector, if you remember, is equal to 1. So these three orthogonal signals play the same role in signals, just like unit vectors play a role in vector space. Okay, so this was just for an explanation. Now you have three orthogonal signals using the process that I just used from these lectures that we studied. So now what? I have three orthogonal signals. Now what I can do is I can define a signal space using these three signals. Since I have three orthogonal signals, this means I need to define a 3D space So this is a 3D vector space, because now I'm converting signals into vectors. So I've drawn a 3D shape, 3 dimensions, because I have 3 orthogonal functions over here. You can say this axis represents f1, this axis represents f2, and this axis represents f3. Okay, so this axis represents f3. So this is our standing right now. So if I have this vector space, or I have these orthogonal signals, then I can represent these 4 signals using these 3 orthogonal signals. So as you can see, S4 can be made with the addition of f1 and f2 and f3. So I do not need to find out additional fourth orthogonal signal, because this signal can already be made up from these three signals. Okay, so that is why I did not find out as F4. So you will use this practice in future as well. Okay, so let's first draw S1. If you notice, if I multiply this signal F2 by under root T by 3, if I multiply the signal with this value, the magnitude will become 1. Sorry, if I multiply this signal with F1, the magnitude will become 1, and from 0 to T by 3, I'll have a signal with magnitude 1. So from 0 to T by 3, I'll have a vector with magnitude, signal with magnitude 1. So I say that if I multiply F1 with under root T by 3, I will get S1. Okay, so this is actually a vector from this point up till this point. Okay, so this is how I have converted S1 as a signal into S1 as a vector. Okay, now it's very easy to draw S2, S3 and S4. I will draw S2 as well. The S2 is a sum of these two signals. If we add these two signals, we will get S2. However, we have to multiply F1 with under root T by 3, and we have to multiply F2 with under root T by 3 to make sure that we get the one magnitude for S2. Okay, so we say that we multiply F1 with under root T by 3 and we multiply F2 with under root T by 3, and this point, this specific point is actually now S2, because S2 is composed of F2 and F1, and we have to multiply F2 with under root T by 3, multiply F1 with under root T by 3. So this is the second vector representing S2 now. So I'm sure now you can see how we can make S3. S3 is made up of only F3, because is it? No, it's not. S3 goes from under root T by 3 up till T. So and from T by 3 up till 2 by T, 2 into T by 3 we have F2, and from 2T by 3 up till 2 we have F3. So if I combine these two signals, I get S3. Okay, so S3 is made up of F2 and F3. So S2 is made up of F2 and F3. I have to multiply F3 with again under root T by 3, and this value and this value, when they meet up at this point, it makes S3. Okay, so now S4 remains. S4 can be made by sum of all these three signals. So S2 is actually in F2 F1 plane. F1 is only S1 is only on F1 axis. S3 is on F2 and F3 plane, and the S4 signal, since it is made up of all these three signals, so the S4 signal will be present as a 3D vector in F1, F2, F3 plane. Okay, so you can easily multiply these three values under root T by 3 with these vectors, and this fourth signal S4 will lie somewhere over here. Okay, none of the signals is actually on the negative side. There is no signal on minus F1, minus F2 or minus F3, because all the signals over here are positive. If one of those signals, for example, was negative like this, then I have to multiply one of these vectors, one of these orthogonal signals with a negative value. So one of these axes would go on the negative side. So that's not the case right now. So I hope you can draw S4 very easily and point it out. And we have this vector space. Now, what do we do with vector space is the topic of discussion in the next lecture for the next week. Right now, all we have to do is that we appreciate that if we find any signal set, then we can find the orthogonal signal space that is representing these signals. And we have found a process, the Gram-Schmidt process, through which we can make this discovery. Okay, so if you can practice this problem for with the provided document of Georgia Tech University, and from the book as well. It has the example as well, so you'll understand all these values very easily. Just for reminder again, our textbook calls these signal as x1 and x2 and x3, and calls these orthogonal signals as phi1t and phi2t, but the document calls it as f2. So that is the only difference in the notation, and rest all is the same.